Um, this series will talk about firstly intro to different terms used in body plot. Then we'll do an example, and then we'll talk about controller design, different compensators. So I'll just talk a lot on here first. So the reason why we use body plot is because for Nyquist plot, right, you may not have enough things to draw, right, not enough information, or it's not accurate enough. So therefore, you use body plot. Similarly, Nyquist plot and body plot, they can plot for gain and phase, as you can know from Nyquist. We're talking about gain margin and phase margin. So in this case, body plot is also talking about such, but you are drawing graph in terms of gain. Okay, this is gain in terms of phase. So in this series, we're going to talk about transfer function. What are the different terms in the transfer function, and then we can start from there. So in order to do that, you have to first know that this is the equation for the gain margin. I mean not gain margin, but rather the gain equation. Or this is the equation to get your phase equation. So typically you will have two graphs, one for gain, one for phase. Right. So in order to do that, transfer function comes in. So the transfer function comes with a controller itself, the K. We have your zeros, and we have an integrator. Okay, integrator can be squared to the 3 to the 4, so in this case they write x to the power of r. So 1 over s to the power of something is the integrator, if you remember. So this is the zeros, this is the poles, sorry. So the denominator are the poles. So with this concept, there will be a different derivation for different type of this parameter. So from this case, you can know that there is 4 parameters: the controller, the poles, the zeros, and the integrator. So with this said, what we're gonna do is actually to translate. Be mindful that this video is talking about only different terms. Okay, I'm not gonna do examples. So examples wise, later. So this is just a general concept of it. So in this case, the transfer function g of s, right, includes your controller k, right. So if you were to know that s is equal to j omega, right, if you remember, so j omega is actually over here. So it's just simply switching s to j omega, right. Uh, s equals to j omega if you remember. So this is after which you can actually absolute them. Okay, you modulus them because you only want the positive values. The reason why you want positive values is that I'm talking about positive frequency. So positive frequency, you're gonna use positive values. Nonetheless, in the more definitive ways, I can't explain. So in this case, your 1 plus s over omega z1, right? Your s over here, you're gonna change to j omega. Similarly to your s over here and your whatever, okay, whatever s's, you're gonna change them to whatever j omega. So this is simply that system, right? So so what is this now, right? So this is actually your gain, right? If you remember just now this equation, if I were to bring this down, this is the exact thing we're talking about the gain. So if you're gonna draw a gain body plot, you're gonna use this equation, right? 20 log then g your transfer function. The 20 is simply a constant. So the reason why I also don't know, but you just use it. So 20 log k. So if you were to do that, right, what you're gonna have is that you're gonna have a positive 20 log k, right? So it's this terms over here, because you're gonna take 20 log of the whole transfer function over here, right? So in this case, if you remember the log rules, is that if it's like a times b, if you were to log them up together, you would get log a plus log b, right? So if there is let's say if it's log a divided by b, you're gonna have log a minus log b. So this is the case behind what is this thing we're trying to do. So in this case, as I mentioned earlier, there is 4 terms. This is the controller k, this is the zeros. This is the integrator, this is the post. So whatever thing at the denominator, you're gonna have a minus, right? Based on the logarithm rule equals to log a divided by b, you get, this type of thing. So this is simply so this portion over here is simply this portion over here, where this portion over here is actually this portion over here. Right, it's just how they do it in that manner. Right, so then you got a transfer function. Alright, the first thing you're gonna do is actually to come out this equation. Right, this is only for the gain portion. For the phase portion, you're gonna have this equation over here. Right, so it is let me see. If you remember correctly, if you look at an Argand diagram, this is the real axis, this is the imaginary axis. Tangent inverse imaginary over real, you'll get some angles, right? So this is the phase angle, I would say, right? So let's say let's say I have a value. In this case, since our real axis is actually 1, and then my imaginary also over here. So you're gonna take imaginary, which is let me see. Okay, so you're gonna take the angle over here. This is actually the angle that I'm talking about, theta, phase angle. So you're gonna take the imaginary, which is opposite, O divided by A. So this is how the Tokaso works. So opposite over adjacent. So the opposite is actually imaginary over the real axis. So you will have these things. However, because what we have over here is actually the real axis is always 1 plus something, right? So in other words, normally what you're gonna do is actually to set it out to 1 plus s, to something. So at least in a certain way, it's easier for you. Maybe in the later examples, we'll see whether do we really need to change to like 1 in this case. So as you can see, the real axis is 1. So therefore, imaginary, as you can see, imaginary is actually omega over omega z1. Later soon you will know that this is actually the corner frequency. So this whole thing is actually the imaginary axis, right? Divided by 1, you'll get back this over here, right? So this is why we explains this is the first zeros. Okay, so this thing over here is the phase angle of these zeros, right? So, and then you add on with the angles over here. So it's very similar to your Nyquist plot. Is it Nyquist? I think Nyquist lah. And yeah, so this is the case. And then I wonder why I didn't include the k, since you say that there is four terms. The k itself is actually only the real axis, right? It's only talking about the real axis. So imaginary is 0, right? So 0 divided by anything is actually 0. So tangent inverse 0 is actually equals to 0. So therefore you have nothing over here, right? So this is only for the zeros. I mean the poles and zeros of the zeros of the poles and zeros, not the 0 that I'm talking about, the value 0. But yeah, so this is the integrator. Okay, this is the integrator part. R times 90 degrees. Okay, what this means is that if you remember our integrator, 1 over s is equals to minus 90 degrees, right? So if it's 1 over s squared, you will have minus 180 degrees. 1 over s cubed, you will have minus 270 degrees, right? So in this case, the the higher order you have, maybe like this is like n, then n plus 1, n plus 2, right? So this is the thing is talking about lah. So if you got 2 in the exponential terms, you're gonna multiply by 2. If it's 3, then you multiply by 3. So this is the thing. So yeah, and in fact you have to memorize all those lah, because it's not given a test. So yeah, and then this is simply the poles. Okay, it's just simply trying to translate the poles. So these are the poles, and then the others. So this is the integrator. So therefore, I hope that I give you a clear view of the different four terms in a simple transfer function. Okay, the controller, the poles and the zeros, poles and the zeros, and the zeros. I mean the zeros and the poles, sorry. And then this is the integrator 1 over s, or whatever, 1 over s squared. So in the next video we'll talk about a more in-depth one on the simple plotting of it, and then we can do some examples. I see you there.